Hi, today I'll go over a data structure called B+Tree. Now, what is a B+Tree? Well, a B+Tree is just like a regular B tree, except that in a B+Tree, you have all of its data contained down at the bottom leaf nodes. As you can see here, 1, 2 are contained in this leaf node, 4, 5, 7 are contained in this leaf node. And you see the leaf nodes are actually connected, linked, just like a linked list. This will make range query a lot easier than a regular B tree, which is why B+Tree is more desirable when you're doing a database project. Another difference is that the non-leaf node, in this case we're looking at the root node, the value inside of the non-leaf node is actually keys. For example, if you are to enter 3 next, then this key will tell you that 3 should go into this subtree, right? So it will lead you to this leaf node. In this case, since we only have the level is only 2, we don't really do that many hops. But a good thing about B+Tree is that doesn't matter which direction you go, the distance that you go in order to reach the proper leaf node for the data you're entering is the same. So this often makes you want to make your leaf node contain much data as possible. Also, I want to mention that remember in your B tree that when you have 3 parents, your children, the maximum children it has can have up 4 children. Now, if it's in a B+Tree, the number of data in your leaf node can be huge. You can make it make it contain 3-digit numbers of data, and often that's what you should do when you are using a B+Tree as the data structure to implement the project that you're doing. So in this case, my program that I will demonstrate, I use inheritance in this case. I have the parent node structure, node class, and then I have the child internal node, and I have another child called the leaf node. Now, the minimum keys per node here I set it to 2. The maximum key per node is 2 times 2. So in this case, it will be 4. That means, unless if you're using this website, that means the maximum degree should equal to 5. When you're entering the 5th value, that should split the node and make it grow a level in this case. And the maximum data, which means the maximum leaf node data capacity, is also 2 times 2, 4 in this case. Now let's run the program and let me explain how the print function works. Okay, here, let me clear this. I'll be entering numbers, integers in my program, them on the website as well. So here I'll enter 1, and then I'll print the tree. As you can see now here, you see the 1 that's contained inside of the bracket. That means whatever inside the bracket means that's the value in the node. And the number 3 means it's a leaf node. Any number that's other than 3 means it's a non-leaf node, which that could be either the root or internal node. And this number 1 here represents that there is only 1 number in this node, which is true. Now I'll enter another number 2, and I'll print the tree. And you can see that the node contains 1 and 2. It's still the leaf node, but now the number of keys contained in the node becomes 2. Now I'll enter 3, and I'll enter 4, and then I'll print 3. 1, 2, 3, 4. So now you see it's still the leaf node. Now it contains 4 numbers. Now I'll do that in the website as well. 1, 2, 3, and 4. Now the next number I enter should split the node and make the tree grow a level higher. I'll enter 5. Now I'll print the tree. Now you see 1, 2, the node containing 1, 2 is a leaf node and has 2 numbers. The node containing 3, 4, 5 is also a leaf node, contains 3 numbers. Now the node containing 3, that's a non-leaf node because 2 is different than 3 and it has 1 number. Now let's enter 5 here. As you can see, right? Basically, the minimum of this node, this leaf node went up top. Now the basic algorithm of the insertion function can be found in the Wikipedia. So I will not be reading you the detail, but my insert function is a bit different than the one on the Wikipedia, but it's all up to you. Now here I perform the search here, and then it will return a Boolean value. If the data I'm entering in the tree already exists in the tree, I'll simply return false. Now this can be modified later on to allow duplicate inserts. It can be easily done, but just by definition, I am only allowing unique values in my trees right now. Now, let's try delete. I'm going to delete 3 and print the function. You can see 3 gets deleted. 3 gets deleted. Now this node right now has only 2. And this guy gets pushed up to its parent. Now let's delete 3 here. Now let's delete another number. Let's delete 4. Now when I delete 4, this node, well, this will validate the property of the B+Tree because the minimum value per node is 2. If I delete 4 here, this guy will have only 1 value. So this will call for a merge. Now let's delete 4 and print it. As you can see, they merged, the 2 leaf node merged, and the tree actually lost a level. So now this guy becomes the leaf node and also the root node and contains 3 numbers. Let's delete 4 here. You can see here, the incause merge there. Now the delete function is a little bit more involving than the insert function, but the algorithm for the delete function also on the Wikipedia. So if you can look at it, you can Google it easily. Now another thing I want to be showing you today is our B+Tree on disk. Now Wanda will have a much more in-depth detail of how this works. What I will do is simply show you how it works, how to make it work on Mac, because it's a bit different on Windows than it is on Mac. So here, let me just go ahead and run this function. Before I run it, I want you guys to know that the tree, the B+Tree is already built in the disk. We already saved the tree in the disk. So if I click this run, it's now loading the tree. It's now loading the entire tree. Here I'm using this file called the tree text. It has number from 10,000 all the way to 48,001, and I also have 3 duplicates of 4,000, the last number. So here I will traverse the tree one time in ascending order, and then I will find everything. I'll print everything in the tree that's less or equal to, in this case, 38,000, and then I would find out the objects in the tree that's equal to 38,001. Well, in this case, let's do 4,801. So I'll run this program. And there, it's traversing the tree. As you can see, it traversed the tree one time. It's traversing the tree in ascending order. Now, you see, since we have 3 insertions of 38,001, so it's telling you that position, there are 3 different positions. And now we're traversing the tree, which is less, or printing every key that's less or equal to 38,000 here, including 38,000. And then we'll find the tree which is equal to 38,001, which we have 38,001 and then its positions. Since we have 3 insertions of 48,001 in the file, we have 3 positions. Right here, 1, 2, and 3. And here it shows 3. Now, in order to rebuild the tree, rebuild the tree, what you have to do is you need to delete this header file. This header is hidden, so if you don't have the show hidden files, you need to enable that in order to see this file. So you simply, all you have to do is delete this guy. And you can delete this column folder as well. And so what you have to do is simply just recreate the folder. It's taking a while. A minute's enough. All right. So let's create a new folder called column. Now the reason why we create this column is because the program is designed to save all of the column files, which every column file is a binary file that contains a single node. So we simply want to save all the column file in this folder so that it doesn't crowd the main directory and make it messy. So here we can see column folder should be empty, has nothing in it right now. So now since header file has been deleted, when I run this program, instead of loading the header, there will be no header to load. You will actually build a tree from the start. So let's do that. This is just a counting of numbers. So there should be 38,004 numbers. When it reaches that number, that means our tree has been built. This will be significantly longer than, say, if you're loading the header directly and just loading the tree from the disk instead of building the tree every time you run the program. It's almost there. If you're dealing with 1 million records, that's going to take at least, I would say, 30 minutes to complete building the tree. But every run after that should be quite fast. Well, unless, of course, if you traverse everything in a million record, it will still take a while, but it will be much, much quicker than this. Right, almost. There, it finishes, and so it traverses that tree, which is the same thing. It still printed, it still traversed the tree, it found all the object that's less or equal to 38,001, and then it traversed and they found the object that's actually equal to 48,001, which is here, same as the first time. Now that when you look at the file again, you see the header file has been created. The column folder has been filled with the column files, which contains all the nodes. So the next time you run it, you'll simply load the header instead of building the tree, and so it will just traverse the tree again. So it's just that fast, much more quicker than if you say you're building the tree every time you run the program. That'll be all for this video. I'll upload the B+Tree on disk very soon. Thank you for watching.